Okay, these are some more of section 9.1, and I'm running just a little bit short of time, so I'm going to go through just my notes and give you an idea of how you can come to the conclusion on some of these. On exercise 3 through 6, tell whether the series is the same as, and this was the series, the summation from n equals 1 to infinity of negative 1 half to the n minus 1, and when n is 1, we've got 0, so that's 1. When n is 1, that's negative 1 half. When n is 2, that's positive 1 fourth. So it just alternates like this. So the alternating series. And we just want to see if these series are the same. So if I look at number 3, if you look at the nature of number 3 in your book, you'll just see that no matter what n is, all the terms are negative. These terms alternate, so definitely it's different, so it's not the same. Tell whether the series is the same. This is not the same because all the terms are negative. These terms alternate, so that's all you have to say. On number 4, if I take a look at number 4, this was the summation from n equals 0 to negative 1 half to the n, and I just worked it out, and it looks like I get exactly the same, so that is the same, so I just worked it out. On number 5, the same thing. Number 5 was n equals 0 to infinity of negative 1 to the n times 1 half to the n, and again I just worked out some terms. This is going to give me 1, and this is going to be anything to the 0 power is 1, so that generates 1. When n is 1, this is going to be negative and 1 half, so this also generates the same thing. So number 5 looks like it's also the same. And then number 6, I took a look at number 6, and I worked out some terms here. Number 6 was the summation from n equals 1 to infinity of negative 1 to the n, 2 to the n minus 1. And I generated some terms, and what I got was, when n is 1, I got negative 1 over 2 to the 0, which is 1. So it looks like I got opposite signs here. And then when n is 2, that's a positive over 2. And when n was 3, I got a negative, and then 3 minus 1 is 2, 2 squared is 4. So it looks like my signs were opposite. So those weren't the same. So that's pretty much all you had to do for that. Okay, for number 7, I didn't really use partial sums. I just used some of the theorems because it didn't seem that it was very explicit either way. But I looked at number 7, and it says compute the limit of partial sums to determine whether the series converges or diverges. Well, I didn't do that. I just kind of looked at the series. And I checked the ratios first of all. So I took the second term over the first term, and I got 1.1. And I took the third term over the second term, and I got 1.221. So first of all, it's not a geometric series. So that's one that you can determine whether it converges or not, determined by the ratio. So I came up with the fact that there's no common ratio, so it's not geometric. So I'm not going to go that route. So I don't have to worry about that. And then if I look at the terms, if you look at the nth term, it looks like you just keep adding 0.1. 0.111. It starts, number 7 starts with 1, and then it's 1.1, then 1.11, and it just keeps going. And as you take as the limit as n approaches infinity, it's not going to be 0. And remember, we had one of those special theorems we talked about, that if it converges, and that's over on page 475, and this is an easy way to identify some divergent series. If the infinite series is up on the top of page 475, if the infinite series converges, then the limit as n or k approaches infinity of the kth term will be 0. In other words, this term has to approach 0. Well, it's not approaching 0. As n approaches infinity, a sub n is not approaching 0. You just keep adding 1. So therefore, I could say that it diverges. All right? So that's kind of the way I got around that one, rather than writing out all those partial sums, which you would come to the same conclusion. You can't get that limit. You can't find a limit there. The limit doesn't exist. It just keeps getting bigger. Okay. Number 8. If I look at number 8, this was 2, negative 1, plus 1, negative 1, plus 1, negative 1. So it just kind of alternated. The partial sums alternate between 2 and 1. In other words, if you take the partial sums, 2 minus 1 is 1, and then 1 plus 1 is 2, and then 2 minus 1 is 1, and then 1 plus 1 is 2. So the partial sums alternate between 2 and 1. All right, so there's no limit as n approaches infinity. It's an oscillating situation, so you don't have a limit. All right, number 9. Number 9 was a real nice one, and this was, I mentioned this in class, that a geometric series is one of our most important ones. And if I look at it, I got 1/4, 1/8, 1/2, 1/4, 1/8, and it looks like my a sub 1 is 1/2, and looks like I have a common ratio of 1/2. In other words, if I multiply 1/2 times 1/2, I get 1/4. If I multiply 1/4 times 1/2, I get 1/8. And it looks like this is the nth term. So it is a geometric series. All right? And all we have to do is state whether it converges or diverges. Well, what's my ratio? My ratio is 1/2. And remember, a geometric series like this converges as long as the ratio is, or the absolute value of r is less than 1, and 1/2 definitely is less than 1. So it converges. It's a geometric series. As long as you can find a common ratio, you got yourself a geometric series, and that's money in the bank. Probably the most important single series is the geometric series. We'll use that a lot. Okay, and then number 10. I had 3, and then I got 0.5 plus 0.5 plus 0.05 plus 0.005. Now, we can kind of separate this, and we can look at 3 all by itself, and then we can look at the rest of it. Because if it converges, it will just approach a particular number, an identifiable number. So if we just separate the 3, because this looks pretty good from here, because it looks like if I take 0.5, if I multiply that by 1/10, what do I get? 0.05. If I multiply that by 1/10, what do I get? 0.005. So it looks like I have a geometric series from here on, where my a sub 1, or my initial, sometimes they call it a sub 1, or just a, my initial term is 0.5, and my ratio is 0.1. And does this converge? Yes, it converges. We can actually find the value by using this formula, a sub 1 over 1 minus 1 minus r, and then we can just add 3 to that. So since the absolute value of r is less than 1, r is 0.1, then this definitely converges. I can actually find the sum by using that formula. And I mentioned that formula, I think, in class, that the sum of a geometric series equals a sub 1, or a, that's my initial term, all over 1 minus r, sometimes we call it a sub 1, as long as the absolute value of r is less than 1. That's for a geometric series. So my a sub 1 is 0.5, and my r is 1/10. So 0.5 divided by 1 minus 1/10, which is 0.5 divided by 0.9, which is just 5/9. That's the sum of this geometric series, is 5/9, and then I add 3. I actually have the value, so it does converge to that value. That's the sum, 3 and 5/9. Okay? So hopefully that helps on those.